Here we go. Okay. Let's see. Do I have everybody's Facebook? 1, 2, 3. Let's move on. I'll hand them all back when I get this one ready. Next exam. Exam 4, Chapter 6 on thermochemistry. It's always good to understand what words mean, break them apart. Chemistry is what we've been doing since the beginning. Thermo refers to heat. So thermochemistry itself is a study of what happens during a chemical reaction to the heat. And that's usually measured in terms of a heat transfer. Now, in general terms, heat is a type of energy. And energy at its basic, most fundamental level is defined as the capacity to do work or to produce heat. This law is at the very center of studying energy transfers, heat transfers in chemical reactions, the law of conservation of energy. And all it states is that you cannot create or destroy energy. You can only transfer it from one place to another. Another way of putting it is the total energy content of the universe is a constant. It does not change. Now, this refers to every chemical and physical process. In other words, you don't have to have a chemical reaction to get a change in energy. And most chemical and physical processes do not occur unless there's a change or transfer of energy. I can't think of a single one off the top of my head that would qualify as a process that does not require a change of energy, a movement of energy from one place to another. Okay, energy can be subdivided into two groups: potential energy, and that's potential. It just means that it has the capacity to do work. It's not doing work, there's nothing happening, but the potential is there. And more often than not, it's due to either a position, where is the object, relative to some other fixed point, or what's its composition. And in chemistry, this one is usually the more important one. Physics, this is usually the more important one, position. But chemistry is composition, because in the composition of a compound, you have to create, or when you make the compound, you have to create and break bonds. And those bonds are places where energy is stored. So that's why potential energy in chemical terms is usually due to the composition. What substances are you dealing with? Like, are you dealing with carbon dioxide? There's no energy stored there relative to most points of reference. But nitroglycerin, yeah, it's got a lot of energy stored relative to carbon dioxide. The other form of energy is kinetic. Kinetic energy just says it's moving. If something is moving in any form or fashion, it has kinetic energy. And there's one particular formula that applies to kinetic energy. And that takes into account both the mass of the object, and the object can be small as an atom or a molecule, and its velocity. How fast is it moving? So if the mass increases, kinetic energy increases. If the velocity increases, the kinetic energy increases by the square of the velocity. So if you change your speed on the highway from 30 miles an hour to 60 miles an hour, you've doubled your speed. But you've changed the amount of kinetic energy that you and your car possess. You double it. It's 4 times as much. That's why from 60 to 0, it takes 4 times as the distance to stop your car as it does from 30. Okay. And that also translates into how much gas does it take to burn? How much gas do you have to burn to get from 0 to 30 versus 0 to 60? Right? A certain amount to get to 30 miles an hour, 4 times as much to get to 60. Here's another way to look at potential energy of position. And what we're trying to do here is to describe what happens to that potential energy here. Now, when A smacks into B, once we let loose of it, you would expect that if A now occupies B's position, that all the energy that A possessed as a condition of its height would be transferred to B, and B would travel up to the same height as A, which would be up here. And under ideal conditions, that would be true. But conduct this experiment for yourself and you'll find that B doesn't make it all the way up to there. B's going to make it up to that first level. Now, why is that? I mean, did we create energy? Destroy energy in the process? No, can't do that. Our law says you can't do that. So we got to account for it somewhere. Where did it go? When all else fails, look for heat. Look for friction. Certain types of friction. One object rubbing against another will consume some of that energy. And even an object traveling through a fluid, air is a fluid, water is a fluid, will give up some of its energy to the fluid. So when you get up to a certain speed, say 60 miles an hour on the highway, and you're on flat, you're not going up or down, if you let off the gas, what's going to happen? You're going to slow down, right? So why are you slowing down? You've got all that energy built up, you know, you should be able to just coast from here to Atlanta. Yeah?
Is it because of the weight of the car?
No, the weight of the car determines, well, the mass of the car determines how much kinetic energy the car has, right?
Friction on the ground?
Right, friction. Friction comes in many different places. One, a large part of it is your rubber tires against the ground. Right? Rolling friction is relatively small compared to other types, but there's still a significant amount. So as long as you're rolling in a straight direction, there's a little bit of friction. If you try to turn, what you're introducing is sliding friction, which is very high. So that'll eat up a lot of your energy. So if you try to turn, you're going to consume a lot of that energy in heat. Heat your tires and heat the pavement. Other places, engine. Your engine has friction in it. Your transmission has, all your drivetrain has friction. And the other is fluid friction. You're traveling through air. Wind resistance, sometimes they call it. So you haven't created or destroyed energy, but you've converted it into heat. So what do? In order to travel 60 miles an hour at a constant velocity, you've got to put just enough energy, constantly put enough energy through your engine and drivetrain into that vehicle to overcome the loss of friction. Right? So that's why you can't go from here to it. Once you get up to 60 miles an hour, you can't coast to Atlanta. Or to Charleston, let's make it closer. Have you ever gone down, let's see, my mind's going blank. You're on your way to Lewisburg.
Sandstone.
Sandstone, thank you. Going down Sandstone. What do? Don't tell the cops this. I put it in neutral. And pretty soon I'm doing 80, 85 miles an hour down that hill. Where'd that speed come from? My potential energy at the top of the hill is converted into kinetic energy. It's good for gas mileage too. But it removes some of the control of the vehicle, right? Because as long as you've got some friction from the engine, moving parts and all that, you have better control of the vehicle. So don't try this. Okay, so we've described energy, and heat is a measure of the transfer of energy from one place to another. And it's due to a temperature change. Okay? So energy always, they say heat always flows downhill. Energy always flows downhill. In other words, it goes from a high temperature to a low temperature. So when you put two things in contact with one another, the one that's hotter is going to transfer its energy to the one that's colder.
It's like how you're cold during the winter and you get like a warm blanket
Out of the dryer?
Yeah. I'm exhausted, but basically that heat goes away really fast because transferring heat to you.
Yeah, yeah. And we can never measure absolute heat. In other words, when I say this thing has so much heat, how do I know that? The only way to know it is to compare it to something else. We measure heat based on the temperature difference between two objects. So you measure the transfer of heat. And we use a symbol for that. It's called delta. Delta refers to a change in. So in order to find delta something, we could have delta E for energy. You need to have what's its final energy situation minus its initial, and that gives you the change. Okay, we're going to introduce a couple of terms here that, well, let's take the easy one first. Work. Does anybody have physics? Okay, good. So what's the definition of work? It's a force. You have to have a force acting through a distance. Right. So if I push like this on that wall, am I doing any work? Nope. I got the force, I don't have the distance. If I can move the wall, yeah, I'd do some work. Right? I can't do that. So that's the strict definition of work, force times distance. And we're going to use that formula again later in modified form to apply it to chemistry situations. So once we've used it to do that, then we just kind of set it aside because it's served its purpose. Now, the difference between a state function and a path function. These are important distinctions because of the calculations that we want to do later on. A state function means that all you have to know to define the system with a state function is what is its present condition? What is its present state? You know, you can define it in terms of what's its temperature, what's its phase, and those types of things. That's a state function. We don't have to know where it came from or where it's going. A path function, it does matter where it's been and where it's going, the path it takes. In other words, let's use Beckley to Charleston again. So let's say Charleston's down here And we know Beckley's up here somewhere. Charleston. Okay. So our height above sea level in Charleston is what? 500 or 700 feet, something like that. I'll just guess. Say it's 500 feet. And Beckley is about a half a mile. Let's say it's 2,500 feet. So between Beckley and Charleston, you drop 2,000 feet, right? The potential energy up here minus the potential energy down here gives you the change in potential energy. In other words, you lost the potential energy from here to here. It doesn't matter how you got there. It's still the same amount from there to there. All right? So that's your change in energy. Change in energy, or energy, is a state function. It only matters that you went from there to there. You have a certain state here, you have a certain state there, and the delta E is the change in state from there to there. Okay? Now, what if we want to come back from Charleston to Beckley? Right? If we go up I-77, right? It's more or less, well, it curves a little bit, but for argument's sake, let's say it's a pretty straight shot. But if you go through Montgomery and back up toward, let's see, where do you end up? Oak Hill?
Yeah, you can either go to Kill or instead.
Yeah. So if you go up that way, you're going to be going like this, right? Okay. The work that it takes, the force times your distance from here to here is different than from here to here, right? So work is a path function. This is state, this is path, okay? So when we use those terms, you can think of that analogy. Does it matter the path that you took to find out this value? No. Does it matter the path you took to find out this value? Yes. It takes more work to get up there. That's why we try to produce straight roads with gentle grades. It takes less work to do that. And in some cases, if you don't have a gentle enough grade, it won't happen. Like for a 100-car locomotive, right? You don't, what they try to do with railroad is if you've got a coal car with 100 cars on it and they're all full, and you've got what, 3, maybe, or maybe 4 locomotives hooked up to it, they don't want a grade that's more than 0.5%. So I guess I have to define what percent means, right? Does anybody know what it is? You want to tell me? What's a 0.5% grade? Okay, say this distance here is 100 feet. This distance here is 1/2 foot. Okay, that's a 0.5% grade. In 100 feet, you climb 1/2 foot. So that's a very gentle grade for a coal car with 100 cars back there and you're trying to pull it up a grade. If you go much over that, you're going to strain the engines to where they burn up, or the motors, your traction motors might burn up. So that's the idea. That's why when you go along and you see this railroad over here on the other side of the river or the creek, you're going like this, but they're going only like that. And then further down the line, you might see that track again, but they had to do this thing, cut a few tunnels, take a gentle grade over here, and they end up where you are, but they had to do it at a gentler grade. So it took more work. to get from one place to the other. But in the process, the same amount of energy would have been used. Now, of course, comparing your car to a train is slightly different. There's more energy stored in that train than there is in your car. So I'm kind of stretching the analogy here. All right. So just my luck, we're going to run out of time. Okay, but these initial points are very important. So we have to define our terms. What do we mean by a system? A system is any part of the universe that you define. You got a problem, you want to solve the problem, you define the system. Sometimes the problem helps you define the system. Okay, and I'll explain what I mean in a minute. But we have a system here, and then we have surroundings outside it. Now, in the most general terms, this system is something, and the surroundings is the rest of the universe. But sometimes we want to define the surroundings also, right? So we can say this, and we don't care about the rest of the universe. Okay? And when we do that, we have to take other things into consideration, right? So when we define the surroundings, we've got to know, is our system open? And our defined, let's say our defined universe. This is our universe with a small u, as opposed to the real universe with the capital U. So this is our universe. So is this universe open? That is, energy can cross the barrier and matter can cross. And this one also, is it open? Can energy and matter cross? Both.
With the system?
Yeah, I mean, that's not a question you have to answer.
Oh.
It's a question that you have to ask yourself. Defining your system and surroundings. I'm just defining terms here. There can be an open system. There can be a closed system. If the system is closed, then matter can't cross, but energy can. And sometimes we define our system in those terms. And then our universe, perhaps energy can cross, but matter can't. But this is more often the one that we pick, the isolated. Right? We want, if we're going to define our universe, we need this boundary to be isolated. Right? We don't want energy or matter to cross that boundary. Right? That's most often the choice. Now, in here, sometimes you can allow for a closed system. You allow energy to transfer, but you don't want matter to transfer. But some chemical reactions, you have to allow both to happen. But in those terms, you need to know what your system is and what the surroundings are, so that when the process occurs, you can account for all that movement. Okay? But in general terms, when we define our universe, it's going to be isolated. Right? Nothing crosses that barrier. All right. So, let's define our terms. When we talk about transfer of energy or transfer of heat between surroundings and a system, we need to define what's the sign on that value. Because if we put a number to that, we need to say, is it positive or negative? Everything is defined in terms of the system. If it moves this way, it's a positive. If it moves that way, it's a negative. Okay, always defined in terms of the system. And just a restatement, any energy that leaves the surroundings and enters the system any energy accounted for in the system has to come from somewhere, right? So if it goes in here, the surroundings had to lose it. If it goes out, the system had to lose it. Okay. It goes back to that we can't create or destroy. We have to account for everything. Nice budget. So, accidentally pressed the button again. Let me see. Okay, so the terms. If heat is flowing into the system, it has a positive sign, that's endothermic. Means it goes, endo means into. It goes into the system. And the opposite of that is energy leaving the system. Negative is exothermic. So when we do calculations, and you end up with a negative value as your answer, it's exo. If you end up with a positive value, it's endo. So when we are trying to solve a problem in thermochemistry, you have to do those two things. Define what your system is, define what the surroundings are. Then, which way is the heat flowing? And that depends on temperature difference. Right? If this one's hotter than that one, then it's going to flow that way. If this one's hotter than that one, it's going to flow this way. So for freezing water, I already gave you the answer. What is our system? Well, it's the amount of water that you have contained, right? And surroundings is whatever is outside. Now, for that water to freeze, which way does the heat have to move?
Out.
Right, it has to go this way. Why? Because the temperature has to drop. Temperature's got to be lower out here for the heat to transfer that way. And in the process, the temperature here drops. And when it reaches 0 degrees centigrade, it freezes. So that's an exothermic process because of the direction of the heat flow. Developing an intuition for what's exo and what's endo is something to be desired. All right. I've only got a half hour left. I don't know if I can finish in that time. Let's see how quickly we can define these as exo or endothermic. In this case, the slide tells you what the system is. Right? So in this case, your hand is the system, and it gets cold when you touch ice. So what process is that? Well, if it's a system, and it feels cold, that means it's getting colder. So which way is the heat flowing? Out. So that's exothermic, right? If ice gets warmer when you touch it, in terms of the ice, heat's moving into it. Endothermic. Water boils in a kettle being heated on the stove. The water in the kettle is your system. And if it's changing phase, if it's turning to a gas, we have to what? Add energy, which means increase temperature. Endothermic. Water vapor condenses on a cold pipe. So the water vapor, we're calling our system. And in order to condense, it has to give up heat, doesn't it? So it has to be exothermic. And ice cream melts. Endothermic, right? It's changing from a solid to a liquid, and you have to add energy to it. Okay, good deal. Now I'll leave that there. I might need it again. So let's see if we can, we have the system defined for us in the other slide. In this slide, let's see if we can take the description and define what system would best give us answers to any questions about it. Okay? So, methane is burning in a Bunsen burner in a laboratory. So what's the system first? The methane gas and the air, right? Remember your burner, right? It's got that little thing, that little ring on the bottom, adjust the amount of air. Methane won't burn unless it has oxygen. So the methane with oxygen mixed is our system. Okay? And when the reaction occurs, the surroundings are the laboratory, or your hand if you get it too close, or your hair if you don't have it restrained, will transfer heat out to something else. Right? So that's an exothermic process. And the value will be negative. So many joules produced, per mole of methane will be a negative value because it's exothermic. Oops. Okay, it's not going to give us the answers. You have to take my word for it.
The methane, like the heat transfer, would be negative.
Yes. To the room, to the surroundings. Mm-hmm. Well, and the burner itself. Right? The burner gets hot. I mean, after you shut it off, I don't know if you'll try it, but try to grab the burner before it cools off. You find that pretty quick. Okay. So water drops and sits on your skin after swimming, and then it evaporates. What are we going to call the system?
The water drops and your skin.
The water drops. Because, look, the water evaporates. Your skin doesn't evaporate, right? So it's just the water that falls on your skin. And as it evaporates, you can feel it cooling your skin, right? So your skin would be part of the surroundings. And the water vapor that evaporates is drawing heat from your skin. So it's endothermic. The value of the transfer would be positive value. And your surroundings would get cooler. Okay. We'll have to erase this. Need the space. Okay, hydrogen gas and oxygen gas react violently to form water. Okay, hydrogen gas and oxygen gas react to form water. It doesn't say what form the water is in. So it's not important right now. It may become important later, but not right now. So think of the space shuttle engine. That big orange tank on the outside, it's actually two tanks in one. One tank holds liquid hydrogen, and the other holds liquid oxygen. But in the engine, by the time they get to the engine, they're both gases. They're mixed together and they produce water. Okay, if it gives off energy, so say the best way to think of a problem like that, which is lower energy, the mixture or water, find out where does your energy go, right? So is energy a product or is it a reactant? It's a product. The system gets warmer, releases energy to its surroundings, right? It actually gets very warm. In fact, it gets so warm that they have to flood the launch pad with water to keep it from melting. That's what all that steam is about, all that smoke and stuff. Because hydrogen and oxygen burn together, you can't see them. They're invisible. So all that smoke and stuff you see is steam. Well, they're dumping water in there to keep the launch pad from melting. So when these are combined, they produce water plus energy. Now the thinking part's, the hard part's done. Once you've determined that, then you can use that to answer the question. Yes,
Like steam,
steam vents,
steamboats.
steamboat, yeah. Okay. That's a little more complicated than a rocket engine, but it works on the same principle. Okay, well, I didn't balance this, so let me say, there's 2, I need 2 here. I need 2 here. Okay. So, if energy is a product, what does that say about the difference in energy between these 2 together and that one? Which one's lower? You can't create or destroy energy. So if you've got extra energy on this side, it had to come from somewhere. These 2 together are higher energy state than that one is. Okay. High energy, low energy, here's the difference. Okay. Actually, that's a very important slide. More important than I thought when I first pulled it up. So water has the lower amount of energy. And that's one of the driving forces for the reaction. It's going downhill. High energy, all you got to do is get them started, and they'll just go whoosh. So lower energy here, but the difference is that. Okay, so now we're getting into chemistry. All right. Thermodynamics is a term that's used for the study of energy conversions, either physical or chemical. And it comes into play especially for steam engines. Or steam engine is a special case of what we call heat engines. If you generate heat in any form and transfer it from one place to another, you have the potential to extract some of that energy out for useful work, like to move your vehicle down the road. That gasoline engine, it used to be that gasoline engines were at best 15% efficient. So all the energy that's contained in your gas tank, you only get about 15% of it to move your car. They're doing better now, 20, 25%. But it's still inefficient. So where does the other amount of energy go? It's just lost to heat. And we'll talk about that. I'm not sure if we get it in this one. That was mid-second semester. You'll see that again, so don't forget what you learned here. We're going to take that and expand upon it. Okay. The law of conservation of energy is often referred to as the first law of thermodynamics. And stated in its simplest form is the change in energy for the entire universe is 0. That just means we haven't created energy, we haven't destroyed it. The final state of total energy in the universe is the same as total energy before. Right? So if you want to go to extremes, like all the energy that we had at the Big Bang, it's still there. It's just not concentrated in a little tiny spot, spread out over billions and billions of light years. Right? So it can get more diffuse, but the total amount is still there. Now, there are pockets, concentrations of energy here, here. So we can exploit those differences in energy, and that's how we extract useful work from it. Right? As it moves from here to here, higher energy to lower energy, we can extract some of that work. But we can't go backwards. Right? Once it's down here, it's either there or it's going lower. Okay? And that's the other topic that we'll cover in second semester. There's a fancy word for it, but I'm not going to fog your brain with it right now. Okay. So we talked about energy. It's often useful to describe systems in terms of how much energy does that system contain in the system, called internal energy. What's in the system? We have to account for both the kinetic and the potential energies, right? So the kinetic energy of the particles in there is just how much energy they have based upon their movement. You know, how much do they weigh? What's their mass? How fast are they moving? Well, as you may have guessed from Avogadro's number, that if you have a mole of them, you got 10 to the 23rd, right? So we can't watch every single one. We have to take an average value. And the average value of the kinetic energy of all the molecules in a substance is proportional to its temperature. That's what temperature means. It's a measure of the average kinetic energy of all the molecules in a substance. Potential energy is a little more difficult, and it's not unattainable, but the internal energy is, in terms of its potential energy, is usually tied up in chemical bonds. Or if it's a gas, it could be tied up in the compression effect. So if you push down and compress a gas, you're storing potential energy in that gas. And if you let go of that plunger, and the system is frictionless, of course. If you let go of that plunger, it's going to come back and smack you in the head, right? Because it's releasing that potential energy. So it's not all in bonds. It can be in, especially for gases, it can be in compression. But there are two terms that define the internal energy of a system. And they are Q and W. Q refers to heat, the heat of the system, and W is work. Those two will account for all of the internal energy. Right? Now, we just said that the internal energy can be potential and kinetic, and that's true, but this doesn't tell you where it is. You know, part of it could be in here and part of it could be in there, right? So there are two different concepts that I'm throwing at you. Heat and work. So how do we measure the heat? Well, we have to measure it in terms of a transfer. If we want to know how much heat is in the system, then we need to transfer that heat from the system to the surroundings and measure the change. And we do that with a change in temperature. Okay. Whereas work, we measure initially in terms of force times distance. So you may guess that the easiest system to deal with in terms of work is a gas, because it allows you to apply a force through a distance when you compress or when it decompresses, one or the other. It's a little more difficult to gather that information for liquids and solids because they're virtually incompressible. Now we know that some liquids, like water, is compressible. All we have to do is measure the density of water at 2 miles below the surface of the ocean. And you'll see that, yeah, it is compressible. But back to the topic. So we measure this in terms of temperature change and this in terms of force times distance, initially.
Relationship between the internal energy of a system and the energy flow into it. Dynamics gives the relationship between the internal energy of a system and the energy flow into and out of the system. This example shows a system where heat enters by the system. Internal energy remains constant if there is no friction. If instead of adding heat, we do work on the system by compressing the piston, then energy will flow out of the system as heat. The internal energy is again constant. Take note of the sign conventions for Q and W. The signs of Q and W are positive when energy enters the system. Here we have a system in which a chemical reaction is taking place. What are the signs on Q and W in this example? Is there a change in internal energy?
Okay, so we still abide by our convention. If heat moves into the system, it's positive. Moves out, it's negative. If work is done on the system, it's positive. And if the system does work on its surroundings, it's negative. Okay? So it was a little easier before when we were just talking about heat transfer. When we start talking about work, you have to think in terms of who's doing what to whom. So if we compress the gas, we're doing work on the gas. So that's positive value. And if we allow the gas to expand, then it's doing work on its surroundings, negative. Okay. Oops. I gotta retake control. I've only got 10 minutes. I want to get to the more important items. This one is recorded already last February. And if we didn't have a lab now, I'd just stay in here and finish it with nobody here. But we'll just have to call it quits when the time runs out because we got to get the lab done. Okay. So in any measurement, I mean, this is the same as chapter 1. You have a number that gives the magnitude of the change. Actually, there are 3 parts here. The number, and you have a sign, and you also have the units of measure. Right? Units of measure for energy or work or any of those quantities is going to be in terms of joules. Right? Now, you may have to modify an answer from one to make it compatible with another one because one may be in terms of kilojoules and the other one may be in terms of joules. So they have to match before you can add them together or subtract them. Right? So always be mindful of that. The units of measure. So in this situation, if Q is positive, we have an endothermic process. And if Q is negative, we have an exothermic. So there, Q would be negative, and here Q would be positive. Similarly, work would be negative if the system does work on its surroundings. It's losing energy by doing that work on the surroundings. Right? So that's like an expanding piston in your car pushing on the tie rod and making the crankshaft rotate. As it pushes, it's transferring energy in form of work to that crankshaft, and that goes back to your wheels and makes you go. Now, this discussion simply accounts for the conversion of the standard format of force times distance in an expanding gas to other units or other measurements of a gas so that we can use those rather than force times distance. So I can't go through this whole thing because we don't have time. But what it turns out to be is work for an expanding or contracting gas is pressure times a change in volume. What that means is the pressure has to be constant. Okay? Pressure is constant, you allow the volume to change. and that is measurable as work. Now, one thing we have to do is apply the sign convention. In order for, since the change in volume as the gas expands is positive, then positive volume, a positive delta V times delta V is positive and pressure is constant. What we have to consider is what's that sign in terms of work? Well, if it's expanding, it's doing work on the surroundings, which means the system is negative, right? But this positive times pressure is going to give you a positive value, right? So to maintain the sign convention, we have to stick a negative out in front of it. So in order to keep work and this expression consistent with our sign convention, we have to stick a negative in front of it. That's why the negative is there. And the only reason is just to maintain the convention so that we don't come out with the wrong calculation. Now, whenever we multiply pressure times volume with standard units, liters and atmospheres, you get liter atmospheres as work. Well, you can't compare that to other measurements of work like change in temperature. So we need to have a conversion factor. 1 liter atmosphere is equal to 101.3 joules. So there's a conversion factor. You have an equivalence, so you automatically have a conversion factor. 1 liter atmosphere divided by 101.3 joules would be one way. Flip it over if you need it the other way. Doesn't matter either way. But that's your conversion factor. And that should be in the review document. Conversion factor. Let's check to be sure. Yep, there it is. About halfway down the second column. So that's another one you don't have to memorize. You just need to know where it is so you can find it. Okay, so if we use pressure times volume as our measure of work, then the volume change here is 3 times pressure is 2, 6. The difference in volume here is see, that's 3 times 2 is 6, and this is 2. Change from 1 to 3. 2 times 3 is 6. So either one is the same amount of work. I wonder if it might be valuable for us to finish this up next Monday. If we do that, all right, I'll tell you what. Let me mark my place. Here. So a week from today is 14th. So we'll pick it up here on Monday. If you have a chance, look at the video from February. It may have even been March by then. It's on YouTube, and it will finish the discussion for us. And what I can do is pick it up here, and then if you've already looked at that discussion before, then I should be able to go through this pretty quick and get through the review problems on that same day. Okay. So the moral of this story is, based on the results of this exam, you better look at that review document. I'll tell you right now, all those problems came straight out of the review document. So if you didn't look at the review document, you were shooting yourself in the foot. Okay. That's why I said, look at the review documents. Okay. So did anybody bring a tire pump today? No? Okay. I've got a foot pump and I've got one that hooks up to a battery. So since we're a small group, we should be okay. You just break into two groups. And if you juggle your time, right, you could both use the power pump. Because all you got to do is get it up to pressure, then you can turn it loose and go do your thing while the other group pumps theirs up. So I'm going to stop this recording. So let's pick up where we left off in thermochemistry. It would help if we had something to look at. There we go. Let's see. I think that's good. Pretty good. All right. So let's look at the, see if we can determine the sign of the change in internal energy for each of the following under those conditions. An endothermic process that performs work. So let's say we have a system. Okay. And we have our surroundings that we have arbitrarily defined. Isolating this system and surroundings together. So, an endothermic process. What does endothermic mean? Well, endo, of course, everything is referenced to the system. So if it's endothermic, that means heat is moving in. Right? So there's your Q for heat. Which way is work going? The process performs work. So we assume that that means the system is performing work on the surroundings, which means work is being done that direction. So what would be the delta E? And just for memory purposes, right? The internal energy is based upon change, whatever happens to the heat and work. All right. So we add these two together. What if this one is bigger than that one? So this is negative, and this is positive, right? So in that case, if work is greater than heat, then the positive would predominate. And in that case, delta E would be positive. Okay? Whoops. How'd that happen? Work is greater than heat. Okay. Work. Oh. Okay. Caught me in a flub. Try this again. That means this one is positive, this one is negative, because it's leaving the system. Okay, so work is negative, Q is positive. Right, now, if work is greater than heat, then this one predominates, and delta E is negative. If heat is greater than work, then this one is dominant, and that makes delta E positive. Okay. So next situation, that was A. So let's make room for the next situation. Work is done on a gas and the process is exothermic. So if we're doing work on the gas is the system. So if we're doing work on it, that makes it positive. And if it's exothermic, that means heat is leaving, so it's negative. Right? So now if we say that delta E equals Q plus W, and W is positive, and Q is negative, then we just need to know which one's bigger. So if work is greater than heat, if the absolute values of this is greater than that, then that means the more positive one gives you a, let's see, if W is greater than Q, absolute value, then that means the W, or the work, predominates, and delta E is also positive. So that means the internal energy of the system is increasing. The other way around, so if the size of W is less than Q, then that means this is smaller than that one in absolute terms. This one predominates, and that means that the internal energy change is negative. So the internal energy of the system is decreasing. It's losing internal energy in that process. All right. So now we're going to introduce a new term known as enthalpy. Up to this point, we've been discussing heat in terms of Q. Now, Q is a path function. That is the amount of heat that moves in any direction over the entire process. It depends upon the path that's taken. And what we're saying here is that enthalpy is similar to heat. In other words, enthalpy is given in terms of heat, but they are different terms. So Q is the absolute amount of heat that's transferred to or from a system, and we know that based on its sign. If it's positive, the Q is being transferred into the system. If it's negative, Q is leaving the system, and is one of the two means of determining what is the internal energy of the system, Q and W. And there it is, restated for you. Delta E equals Q plus W. Okay, so why am I saying delta H, or enthalpy, is different than Q? Think of enthalpy as potential. It is a potential amount of heat, much like internal energy is its potential to do work or transfer heat. And it is a partial measure of the potential energy of the system. Okay? If we know what the internal energy change is, and we also know how does the pressure and volume change in that system, then we can determine what the enthalpy is. So this is a defining equation. Enthalpy is only part of the internal energy. Okay? Well, excuse me. Internal energy describes enthalpy only in part, and we also need to know what, if any, pressure volume changes take place. So we know what delta E is equal to, right? You have to take my word for this one. Change in that term is equal to this one. But if we know what this one is, it's Q plus W. See, so this one is not equal to that one because you have these other factors to be considered. So that's the first step. Enthalpy is equal to heat plus work plus the change in pressure volume. Now, if the process takes place at constant pressure, then this term becomes pressure comes outside, it's constant now, and only the volume changes. Okay? Now, we know what work is equivalent to because we showed that earlier. The work term is equal to minus P delta V. And if we substitute this one in here, right, for that W, then this negative P delta V cancels out that positive P delta V. Those are gone. So what does that mean? That means if the pressure is held constant in any process that takes place, a constant pressure means that delta H now equals Q. Okay. That's only for constant pressure. If you let the pressure and the volume vary simultaneously, then you cannot say that delta H equals Q. So that's why when chemists do experiments, they tend to lean toward holding pressure constant. If you can hold pressure constant in the whole process, then you can find out what Q is. All you have to do is measure enthalpy. And we'll show you how to measure enthalpy later. Okay? The moral of this story is it's easy to get enthalpy and Q, or heat, confused. Okay. Let's say, for argument's sake, that we're studying a process where we have an initial pressure, an initial volume, and initial temperature. Okay? Then after the process occurs, we measure a different pressure, volume, temperature for that system. What we're saying is that with these changes, there are many different pathways to get from one state to the next. And as we traverse those pathways, both Q and W will be different. So that's why we consider Q and W path functions. However, if we're considering enthalpy, or the potential for change of delta E, then all we need to know is what is the enthalpy of the products, what is the enthalpy of the reactants, and we can find out what the enthalpy of the reaction is. So this is an extremely useful equation for determining enthalpy of a reaction. You just need to know what the enthalpy change of products And that's in terms of what did it take to produce the products? What enthalpy was required to create the products? What enthalpy was required to create the reactants from the elements? That's our reference point. Okay, so if it took a certain amount of delta H to make the reactants and a certain amount of delta H to make the products, then all we have to do is subtract the reactants from the products, and we find the delta H for the reaction. And the reason we can do that is because we don't care how they got there. It doesn't make any difference because delta H is a state function. The path that was taken doesn't matter. All right, so let's put this to practical use. Finding the enthalpy of a reaction in this case, we've got propane, C3H8. I'll just tell you what that is. And we're going to burn it. So this is a combustion reaction, which, by the way, is a redox reaction. Oxidation and reduction takes place during a combustion. Okay? We're producing carbon dioxide and water as a consequence of this reaction. And we measure the enthalpy for that reaction at minus 2,221 kilojoules. I'm going to leave out the states here because for this argument, they don't matter. Right? And the enthalpy for this reaction is minus 2,221 kilojoules for the reaction. Okay? Why didn't we put kilojoules per mole? Because it's not per mole necessarily, it's kilojoules for the whole reaction. Now, see the sign is negative. That means that it's exothermic. Right? It produces energy. And we know that intuitively because you burn propane, things get hot. So it's exothermic. It's very exothermic. Kilojoules, that's 1,000 joules. So if we put this in terms of joules, that's 2,221,000 joules. All right, back to my earlier point. Why didn't we say kilojoules per mole? Because it's kilojoules for this reaction, which means in terms of moles, it could be minus 2,221 kilojoules per mole of propane. But for the reaction, it's that many kilojoules for every 5 moles of oxygen, or for every 3 moles of carbon dioxide produced, or for every 4 moles of water produced. That's why we don't say per mole. It's per reaction. Now, what if we want to find out how much heat, what's the enthalpy production for this reaction if we have 5 grams of propane and plenty of oxygen? So we're going 5 grams, right? This is not related to the enthalpy in terms of grams, it's in terms of moles, 1 mole of that. So we have to find out how many moles of this do we have. We need a conversion factor, right? So we need 3 carbons and 8 hydrogens. Right? So a quick flip of the calculator and 4411 grams per mole is the molar mass of propane. And that means 0.113 moles of propane. All right. So if it's this many kilojoules per 1 mole of propane, how many kilojoules is it for that many moles of propane? Right? So 1 mole. So now the moles cancel. And we just say this times that. So I get 251 kilojoules for 5 grams of propane. Well, rounding error. Okay? That is an exercise in calorimetry, keeping track of the heat of a reaction. And calorimetry then is the science of measuring heat of a reaction. So how do we know that that reaction required or produced 222,221 kilojoules? We need a way to measure it. Okay? The only way to measure heat is in its transfer from one place to another. So if we have a container, if our system, this is our system, and then we have the whole system and surroundings is isolated. That means no matter, no heat can cross that boundary. So this is a self-contained universe. What we need to know is what is the temperature change. So we get a temperature change here, and we'll get a temperature change here, and we use that information to say, all right, with that temperature change and some other facts that we know about the surroundings and the system, we can tell how much heat was transferred between the two, either this way for an exothermic or that way for an endothermic reaction. And to do that, we need to know what is the specific heat capacity. Now, why did I leave off specific here? Because first you need to understand what heat capacity is. Heat capacity is a capacity factor. It depends on how much stuff you have, right? So if you have this chunk of iron and this chunk of iron, this one has more heat capacity than that one. In other words, it can absorb more heat before it changes 1 degree centigrade. 1 degree centigrade, right? So it takes more heat to make that one change 1 degree. That means they have different heat capacities. But if we reference that to 1 gram of iron, right? So 1 gram is here, 1 gram is here. They have the same heat capacities per 1 gram. Okay? That's an intensity factor. It doesn't matter how much you have. Specific heat capacity is intensity. Heat capacity is capacity factor. Now, in this case, specific heat capacity was referenced to mass. Right? The mass specific heat capacity. Sometimes it's more convenient to speak of heat capacity in terms of moles. So if we know how many moles this is, we just use the conversion and we can find out what the molar heat capacity is. Those are the only two that you're going to be dealing with in this course. When we say specific heat capacity, we mean reference to mass of the substance. When we say molar heat capacity, then it's in terms of moles of the substance. Okay. So let's see if we can develop some intuition about calorimetry. Say we have two reactants, they're both the same temperature, and we mix them together. And since they start at the same temperature, and the resulting solution is warmer, what does this mean? Well, how do we know they're warmer? Because we have something surrounding them that changed temperature. So heat had to leave the system when we combined those two reactants. That's how we know that it is exothermic, because the temperature outside went up. This is what a homemade calorimeter looks like. And this is basically what we're going to be using in the lab. Right. So what I need to do is first describe it and then tell you how we use it. So this calorimeter has a reaction vessel in here. It has a way of measuring the temperature change within that vessel. And we need this little stirrer, because if we don't stir it, this may be a false reading. It may be warmer here than it is up here, or cooler here than it is up there, in which case we will not get an accurate reading of the reaction. It needs to be uniform, so we use the stirrer. Now, the system is here, whatever is in the container, and the surroundings would be the cup. Okay, and we want that cup to be isolated from the outside. That's our universe. Inside the cup and its insides are our universe. So the surroundings are the cup. We have to account for any heat change in the surroundings. And we measure heat change in the system within the cup. That isolates our universe. All right, so if we're going to measure the change in heat within a substance, right, we need to know its specific heat capacity, S. And this is in terms of joules, change in heat, for every degree centigrade and for every gram of material. So those are the units of your specific heat capacity. Now, if you know how much mass there is, right, that's in grams. So look at that, multiply these two together, grams cancel. Now you're down to joules per degree centigrade. So if this is in terms of joules, heat, then what we need over here is our change in temperature. So when the temperature changes so many degrees centigrade, that cancels that and leaves us with joules on this side, joules on that side. So this is our basic formula for determining the heat transfer in a process, as long as we know the temperature change, temperature before and after, which is what? Final temperature minus the initial temperature. It's always in that format. Final minus initial. It doesn't matter if the temperature goes up or down. If it goes down, the final temperature is going to be less than the initial temperature. But it's always final minus initial. mass isn't going to change. And the specific heat capacity won't change. It is a constant. Okay, a little intuition now. A little more intuition. Suppose we mix two things together. 100 grams of water, right? And that water is at 90 degrees. And 100 grams of water at 10 degrees. What will be the final temperature? We've got the same substance here, water and water. That means they have exactly the same heat capacity. So they're going to change the same amount of temperature as long as the amounts are the same, right? So 100 grams, water, water. So when you put them together, where is the temperature going to be? Is it going to be colder or warmer or somewhere in between? That's right, somewhere in between. But where in between? Well, the fact that you've got equal amounts of the same substance, they're going to meet at the halfway point. So halfway in between these two would be, let's see, 80-20, 70-30, 60-40, 50. They're going to meet at 50 degrees in the middle. Okay? That was simple. But most problems are not that simple. You may not have water over here. You might have a chunk of iron ore. And it may be at a temperature of 300 degrees centigrade, while your water might be room temperature, say 25 degrees. And you might have 250 grams. So what do you do then? Well, we need a method for determining what will be the final temperature. All right. Oops. Back. All right, before we get there, here's another example where we did change the amount. So now we're going to have 500 grams of water at 10 degrees and still 100 grams at 90 degrees, right? So what does your intuition tell you about where the temperature is going to be? Well, which one is likely to have a greater impact upon the temperature? They're both the same water, but this one, there's more of it. So that amount of water has more heat at that temperature than 100 degrees did. So it has a higher heat capacity, the capacity factor. So where is it going to meet? Not in the middle, because there's more of this one. So it weights toward the lower temperature, right? So the temperature is going to meet over here somewhere. And as it turns out, the final temperature is actually 23 degrees. I'm going to show you how we got that, I think. Or I'll do a similar calculation to show you how you arrive at that temperature. Let's see. Let's do this one. All right. Since our universe is isolated from the real universe, then everything that happens inside our calorimeter is isolated and is not influenced at all by the outside. So we contain everything in our little universe. So for the time being, let's assume that the styrofoam cup, the thermometer, and the stirrer have no heat capacity. We'll introduce that term later. So in an isolated system, the change in heat inside that isolated universe, I said system, universe, inside that isolated universe is equal to 0. But it's made up of a change, a heat term for one item and a heat term for another one on out, however many you have. They're all in that isolated universe, and they all have to add up to 0 because there's nothing going out, there's nothing coming in. Everything that happens is inside. So it all has to equal 0. All right. So for this example, we have 50 grams of water at 10 degrees. All right. So one of our substances, say the first one, is 50 grams of water, and that's the mass. The initial temperature is what? 10 degrees. Okay? So it's helpful to write this information down, extract it from your word problem, and put it out here where you can see it in mathematical terms. So that's your initial temperature. What's the question? The final temperature, right here. What's the final temperature? Well, this just says, is it in this range, or this range? We're going to find out exactly what it is. So we don't know what the final temperature is. That's the question, right? All right, how about the second one? What is that? Well, it looks like it's 50 grams iron ball. So this is, that's the mass of that one. This is the mass of the second one, which is 50 grams of iron. And it starts out at 90 degrees. Okay? We don't know the final temperature. But notice, if you leave water and the iron ball together long enough, they're going to end up at the same temperature. They equilibrate. Remember, temperature moves from the hot to the cold until it can't move anymore. And when does that happen? When does it not move anymore? When both are at the same temperature. So these are equal to one another, the final temperature. All right? So now, everything has to be equal to 0. So what's Q1? Well, specific heat of water times the mass of the water times the delta T, which is what? Final temperature minus initial temperature. Then how about the iron ball? Well, we need a specific heat for the iron ball. We need the mass of the iron ball. And we need a change in temperature. So the final temperature for the iron ball minus the initial temperature will give us that term. All right? These are two different terms. That's water and iron. They start off at different temperatures, but they're going to end up at the same. So 0 equals specific heat of water, 4.18 joules per be consistent, joules per degree centigrade grams. Here, mass 50 grams, and TF minus the initial temperature, which was 10 degrees. All right, that's your water term. That's how much heat was transferred into the water from the iron ball. Why? Because the iron ball is hotter. Now, what's the specific heat of iron? 0.45. 0.45 joules per degree C gram Then the mass of the iron ball, also 50 grams. Final temperature that we don't know, minus the initial temperature, which was 90 degrees. That's the hard part. That's where the thinking happens, right there. From now on, it's just crunching numbers. Right? So, what do we do next? We multiply this times that, 4.18 and 50, and that's 209. 209 what? Joules per degree C, because grams cancel. How about this one? 50 times 0.45. That's 22.5 joules per degree C. Okay? Now what's next? Well, we have to distribute that. So this times that is 209 TF. Okay? And this times that is minus, what, 10 times that is 2090. I'm leaving out the units because we know we did it right. They're going to cancel. This one times that one is 22.5 final temperature, and then minus 22.5 times minus 90. I use my calculator for that one. So that's minus 2025. There you go. All right, now we gather our terms. And these two together, 209, 22.5, plus is 231.5 times final temperature. And these two together, they're both negative. So that's going to be 5, 11, 1, 4. Okay? So now what do we do? Well, you get this term on that side, then you can divide by this, both sides, and find TF. So we're going to have 4115 equals 231.5 TF. TF equals 4115 divided by 231.5. That's going to be in degrees centigrade. $17.8. So the final temperature is going to be 17.8 degrees, which makes it C. Well, round it off, 18 degrees. Okay? So that's how you do a calorimetry experiment, ignoring the heat absorption or delivery of the container. Now, when we actually do this experiment in the lab, we will need a term out here to account for the calorimeter itself, right? Because the calorimeter is, if the inside is hot, hotter than the calorimeter, it will absorb heat. The inside is colder than the calorimeter, then it will provide some heat to the mixture, and you have to account for that in order to know what's happening inside the calorimeter and with your reaction. Okay, So put that on hold for a little bit. We're going to look at Hess's law for a second. And Hess's law is a direct outcome of the fact that enthalpy is a state function. If enthalpy were not a state function, Hess's law would fall apart. It would not work. So, all Hess's law says is that when you go from a particular set of reactants to a particular set of products, the change in enthalpy, the delta H, is the same whether the reaction takes place in one reaction step, two reaction steps, or any number of reaction steps. So that sounds fine, but what does it mean? It means that for the reaction that you choose, A plus B equals C plus D, you don't have to do the experiment to find out what delta H is. Right? In fact, what if that reaction happens to be particularly hazardous? Like you got an explosive there that you want to evaluate. All you need to know is, can you combine two or more reactions that are known and recorded in the literature to give you that reaction? Then you can calculate this based on those other known reactions and say, all right, so that's what we expect from this reaction. Then if you want to, you can go ahead and do the reaction. If it's particularly exothermic reaction, you'll want to take precautions, right? Use small amounts or use a protected environment. Right? So it's either good to determine what the delta H is without having to do the experiment, or in that event, it may give you some heads up as to whether this reaction is going to be particularly hazardous and for you to take precautions. So what does that mean? Well, here's an example. Suppose this is our target reaction. Nitrogen gas plus oxygen yields nitrogen dioxide. Okay? This is given just as reference. We know what it's going to be, the enthalpy for that reaction. But can we use two or more other reactions to derive that value? Well, first thing you have to do is, what reactions do you know? And can they be combined in such a way as to give you that reaction? Well, if you put this one, nitrogen plus oxygen yields nitrogen monoxide, and we know the value for its enthalpy is here. It's endothermic. This one, 2 nitrogen oxides plus oxygen yields 2 nitrogen dioxides, and it gives you an exothermic reaction. So if we add these together, like we get that one, we get 2 of these here, and we get 2 of these here, but these two are on opposite sides of the arrow, means they cancel out. They're not part of the reaction. So it's okay to have these in your component reactions as long as they cancel out in the process. So that's the first rule that pertains to Hess's law. If you're going to use 2 or more reactions to generate the target reaction, they have to combine to give you the target reaction. When you add them together, they have to add up to the target reaction. Then you can add up the enthalpies of those reactions, and you can get the enthalpy of the target reaction. And that's all due to the fact that enthalpy is a state function. It doesn't matter what pathway you take to get there. In this case, it was only 2 steps. That reaction gives you the overall. Okay? This is just a graphic representation. This is if you went 1 step from reactants to product. This is how you go 2 steps, up to here, and then back down to here. And the change in enthalpy is the same, regardless of how you got there.
Hess's law illustrates why enthalpy is a state function. For example, we want to determine the enthalpy change for the combustion of graphite to carbon monoxide. Imagine that the reaction takes place in 2 separate steps. Step 1 is the combustion of graphite to carbon dioxide. Step 2 is the decomposition of carbon dioxide to carbon monoxide. The net result is obtained by adding the 2 steps and canceling out like terms. The enthalpy change for step 1 is negative 787 kilojoules. The enthalpy change for step 2 is positive 566 kilojoules. Therefore, the desired enthalpy change for the net reaction is the sum of negative 787 and positive 566 kilojoules, or negative 221 kilojoules.
Okay? Another illustration of Hess's law. So, what do we do if our reactions don't match up automatically? Say we want to add 2 reactions together, but if we add them together, they don't give us our final reaction, our target reaction, in the correct terms. In other words, balanced correctly. So you have to manipulate the component reactions so that they will add together and give you the target reaction. So what do you do if you have to flip the reaction and put the products as reactants and the reactants as product? When you do that, all you have to do is change the sign of the enthalpy for that reaction. Right? So if we went from this one to this one, and we had a delta H, some number, but we needed it to be the other way around. We just had a negative delta H. And that's the one that you add to get your final reaction. So, now, what if you have the reaction written correctly here, but there's not enough of it? So you need twice as much of each one of these in order to add together to yield the target reaction. Well, this is in terms of the reaction as written. So if we double the reaction, we double the amount of reactants and products. That means we double the enthalpy. So you just multiply by the factor that you use to modify that reaction. Okay, this is an example. If you reverse the reaction, let's see. Did I miss a step? Yes, I did. There we go. So if we want to combine these 2 reactions to get this reaction, first question you want to ask yourself is, do you have everything you need here to give you that? Well, let's see. There's nitrogen, there's nitrogen. There's water, there's water. There's oxygen, there's oxygen. There's ammonia, there's ammonia. And notice you have hydrogen on either side. And those hydrogens we want to cancel out because there's no hydrogen down here. So there are 2 objectives. We want to be sure we have all the components we need, plus we want to be sure that the ones that are there that are not in the final reaction equation are canceled in the process, right? So it looks like we need 2 nitrogens. And we've only got a half a nitrogen. So that needs to be multiplied by 4. Plus, the nitrogen's on the wrong side. So we need to flip it. So we both need to change the sign plus multiply it by 4. That's just for the top reaction. Now for the bottom reaction, oxygen needs to be on this side, so that one needs to be flipped. And then we also need 6 waters, so this one needs to be multiplied by 3. So flip it, multiply it by 3, change the sign, multiply it by 3. Then see if they combine. Let's see. Well, it's not going to tell us that. But that's what you need to do. Flip both of them and multiply by a constant factor. So how do we do this in reality? Well, you sort of work backwards. You start with the target reaction and you look for other reactions that have the factors in there that you need. In other words, you scour the literature or you look in a reference manual and you find reactions that have all the components that you need and as few of non-needed components as possible. But if you find those reactions, then you need to have reactions that will cancel out the unwanted ones in the process. Now, that's what you would do if you were working from scratch on your own. But of course, in the context of an exam or a homework problem, you would be given a set of reactions and asked to use those to generate the target reaction. So we sort of limit the scope so it doesn't take forever in a day to find all the information you need. Then you reverse the reactions required, multiply by a constant, and the constants don't have to be whole numbers. They can be fractions, right? As long as you multiply everything through by the same value and multiply it times your enthalpy, then you can use a fraction if you need it. So back to this equation. So if we multiply the reactants through by 4 in this case, and 3 in that case, they've already been flipped. We flipped them before and changed the signs, so now we're multiplying them through by the constants. Then you get these values, add them together, and you should get 2 nitrogens, 6 waters, hydrogens cancel, right? Left side, right side. 4 ammonias and 3 oxygens. Now that you've got that done, you can add your enthalpies together. And that is the enthalpy for the target reaction. That is the application of Hess's law. Now, for another concept that is extremely useful in determining enthalpies for a reaction is the standard enthalpy of formation. It's written like this. Standard enthalpy. Standard means that you put a 0 up there, and a little f means formation, right? So what do we mean by standard? Standard states. So the standard enthalpy of formation is how do you make this compound from its elements in their standard form. So at 1 atmosphere pressure, 25 degrees centigrade, and if it happens to be in solution, 1 molar solution. But you start with the elements. This is hardly useful because most elements are not. Strike that last one. It's just 1 atmosphere and 25 degrees centigrade. I was thinking of something else. The standard enthalpy of formation is how much heat is required or generated for that reaction to give you that compound. Okay? So, if it's a gas, if there's a gas involved, it has to be at 1 atmosphere. Okay, I guess if you've got a solution, it's 1 molar. And all other substances have to be pure, liquids and solids. So what's the standard state of your elements? Well, when you produce that periodic chart as extra credit, you had to tell me the standard states. Most of them are solids, but there are some gases and there are some liquids, right? There are only 2 liquids. Here, there are only 2 liquids on the periodic chart under standard conditions, bromine and mercury. So that's easy. They're the only liquids. The gases, the noble gases, they're not going to react with anybody, so you can ignore them. Other gases, chlorine, Cl2, F2, O2, N2, H2, solids, there's a liquid, solids, okay? So you need to know the standard states. The standard states in order to determine the standard enthalpy of formation for a compound. Why is that so important? The reason it's so important is that we're going to start. Let's do the standard enthalpy of formation first for a compound, and then we'll use it. So how is it written? Okay, let's do an example. Let's say we want to know the standard enthalpy of formation of methane. You start with the product. There's your compound. It's a gas. What does it take to make that gas? Well, once you put that formula down there for the compound, it's fixed. And there's only one of them. It's always a coefficient of 1. So now we need our elements. Standard state hydrogen is diatomic, and it's a gas. At 1 atmosphere pressure, 25 degrees centigrade. But we also need carbon, don't we? Well, carbon is a solid. There you go. Now you have your elements on this side as reactants and your compound as a product. All right, we're almost there. Now, since that can be 1 and the only one, you may have to use fractions over here. So how many hydrogens do we need? Well, we actually need 4, so there's a 2. We only need 1 carbon, so we're done. That's the balanced equation for the standard enthalpy of formation for methane. And all you have to do is look it up, or it'll be given to you in a test. And there'll be a value over here, standard enthalpy of formation. Okay, so how do we use that? Well, in this example, we have methane plus oxygen yields carbon dioxide and water. Okay, in order to find the delta H standard enthalpy for that reaction, you just say, what are the standard enthalpies for the products? And subtract, let's see. They put them backwards. So for a reaction, the standard enthalpy for the reaction is equal to the sum of the standard enthalpies of formation for the products minus the sum, that sigma means summation, of formation for the reactants. Okay? And this summation requires that you multiply by coefficients. This is 1, so it's only 1 times the coefficient for methane. Right? Elements don't have a standard enthalpy of formation. Right? This value refers only to that. The elements don't have a standard enthalpy of formation. So whenever you encounter one in an equation, the value is 0. Okay? So this one's for carbon dioxide. This one's for water. And what happened here that they're not showing you is that for water, where is it here? The standard enthalpy of formation for water is half of that because you had to multiply it by 2 to get that value. This is a pretty bad slide. I apologize. Blame it on the authors. You get what you pay for. I didn't pay for it, so this slide is crap. Okay, this is just restating enthalpy calculations if you have to combine. So we can skip that. And now we can go to this formula right here. Right, it's just what we showed you. And this N, I didn't stick in there. That N is the number of moles. So, and that is the coefficient in the balanced equation. That's all that is. So for each term that's a product, you multiply the number of moles and the coefficient times its standard enthalpy before you add them together in this summation. So how would we do this one? Well, that one's going to be 0 because it's an element. That one's going to be 0 because it's an element. And we show them to you right here, right here. So you really only have to have 2 times this one minus 2 times that one. And there are the terms. And when you do that, you find out that that reaction is minus 368 kilojoules. So that's a really neat way to do it because all you need to know are these individual values here. And you can throw them together using that formula to find out what's the enthalpy, the standard enthalpy for that reaction. Okay. So a very short discussion at the end about energy. This basically is to appease the global warming enthusiasts. But there is some valuable information here. What is a fossil fuel? A fossil fuel, what is a fossil? A fossil is something that you dug up out of the ground. It was at one time usually living, and then now it's not living. But when you dig it up out of the ground, that reference to it is as a fossil. So any fuel that comes out of the ground is a fossil fuel. Petroleum, we pump that out. Natural gas, usually don't have to pump it. You just need to gain access to it, and it comes out on its own. And coal, you have to dig, right? Those are fossil fuels. They've been in the ground for umpteen million years. Other types of fuels, wood. Wood drove the energy economy of man's stay on Earth from the very beginning. We burned things like wood. When we couldn't find wood, maybe we picked up cow pies and let them dry first and then burn them. Other forms of energy, hydroelectric, okay? That has its limitations too, because there are only just a few places on any given river that amends itself to damming and then allowing the water to pass through turbines and generate electricity. So there are natural limits there. This is the one that is virtually unlimited. Or at least there's much more potential here than there is for all the others combined. Now there are what are called green sources of energy, like solar power and wind power, but they're not really green. And the reason they're not green is that in order to produce a solar panel, you have to pollute the hell out of the environment to make the components for that solar panel, right? So it's really not green. It's a very polluting form of energy capture. Plus, you're capturing a very diffuse energy, solar power. Solar is diffuse, and when you capture it, you cannot concentrate it easily. Plus, it's intermittent. On a day like today, of course, you can't see from the video, but on a rainy, cloudy day like today, you're not going to make any solar power, right? So it's intermittent. Same thing for wind power. Wind power is very diffuse. It's intermittent. And, well, for both of them, they're localized. In other words, there are certain places where you cannot economically produce, and I use that term loosely, economically, you cannot produce solar or wind power. You need a windy place, or you need a cloudless place to produce efficiently, either one of these. Now, in contrast, nuclear power, you can run a nuclear reactor for decades without refueling it. And we've got plenty of fissionable material to make nuclear power. We have the technology to make it safe. The problem is we don't have the will. Okay, so here's what you do. If you encounter an environmentalist who is harping upon CO2 and global climate change, okay, ask that person one question to find out if they are serious about these supposed problems, or if they're simply using those to gather influence, power, and control over your life. Ask them this one question: where do you stand on nuclear power? If they're for nuclear power, then chances are that they're just mistaken in their beliefs. If they're against nuclear power, then they are definitely out to rob you of both control of your life and money from your pocket. Right? Just that one question will give you that. You'll know who to avoid and who to just feel sorry for. We don't have time here for me to completely disassemble the global climate change argument, but that's a good place to start. You can look at this graph at your leisure. It just shows that over time, we have become less dependent upon wood, primarily because we burned it all. There's none left, or very little left. And we transitioned to fossil fuels. First, it was coal at the beginning of the 20th century, and then we transitioned toward petroleum and natural gas. And that's where we are now. Primarily, petroleum and natural gas drives the world economy. Without fossil fuels, the world economies would collapse. They could not be sustained. We would drive everyone, or almost everyone, except for a few of the elites, we would drive them into abject poverty, disease, all kinds of misery, starvation, without fossil fuels. So don't let anybody kid you. We need fossil fuels for the foreseeable future. The Earth's atmosphere blankets the Earth. It does many things besides giving us oxygen to breathe. It also creates a certain desirable pressure at the surface of the Earth so that we don't explode from the inside out. It keeps pressure on us. And it protects us from space. Space is a very hazardous environment. Among other things, there are high energy particles and certain types of light emitted primarily from the sun that would be very hazardous to you if you spent time in space unprotected. On the surface of the Earth, you're protected by that blanket of atmosphere, which filters out many of the harmful effects of radiation. Now, as far as global warming goes, it is true that carbon dioxide, water, and other molecules will trap energy on the Earth. In other words, light comes through from the sun, warms the Earth, and it's re-radiated at longer wavelengths. So it comes in as visible light, re-radiated as infrared light, and everybody knows that your French fries are kept warm by those red lamps, those infrared lamps. So we're talking about heat lamps. Infrared is the heat range of the electromagnetic spectrum. Now, we know that carbon dioxide and water and other molecules do absorb that re-radiated energy. The question is, how much of it are they responsible for trapping energy? Well, as it turns out, there's not enough CO2 in the atmosphere, even at today's elevated levels, to account for global warming, right? And for the present, the globe is actually cooling. So that shoots a hole in the global warming enthusiast argument right there. But it's a very complex system. And even the most learned and published climatologists will tell you that we don't know enough to predict what the environment is going to be on Earth 10 years in the future, much less 100. So basically, what I hear from the global climate change crowd, what they're saying is, let's do something now, even if it's wrong. All right, so there's an example of what happens. In order to get significant impact of a global warming type molecule, you need very high concentrations. Perfect example, the planet Venus. Venus has sulfuric acid, carbon dioxide in its atmosphere of huge amounts. So its ability to heat the surface of that planet are significant. but that's a far cry from the surface of the earth. In fact, carbon dioxide is a nutrient for plants. Controlled experiments have shown that if you increase the carbon dioxide level, even beyond the levels that we see now, today, you will get increased production from the plants. They will produce more biomass. And that is with the exact same amount of all the other nutrients and the amount of radiation that they receive. So carbon dioxide is not a pollutant, no matter what the EPA wants to tell you. Carbon dioxide is a nutrient. And a byproduct of plant activity, when they absorb that carbon dioxide, is oxygen. And that's something that we desperately need. Okay, other forms of energy production. Coal can be converted, and the pollutants, the ashes, the sulfur compounds can be trapped and produce a clean fuel from coal, usually natural gas. Hydrogen as a fuel, that's the holy grail. Why? Because all you need is a clean source of energy like nuclear. We've got all the water we need. We can take the water molecule, split it into oxygen and hydrogen. And let's see, 2 here and 2 there. And there's our fuel, hydrogen. Well, plus oxygen is extra. Oops, need to do that. Other sources of energy. Well, fossil fuels, oil shale. That's why the United States now, one of the reasons the US is energy independent, because the floodgates were opened when Donald Trump came into the presidency, removed regulations on fracking. We now have access to huge reservoirs of oil that we didn't before because of EPA regulations and red tape. So now we're energy independent. Other forms, ethanol, primarily in this country from corn. When you produce ethanol from corn, it takes more energy to produce a gallon of ethanol than energy stored in the ethanol. So it's a net loss, ethanol. We would not have ethanol as a product and in our gas tanks if the government did not subsidize it. If the government removed its subsidies for ethanol production from corn today, it would disappear from our gas tanks tomorrow. Methanol is another product. Okay, these are organic compounds. When combined with oxygen, will burn. Seed oil, that's off in the distant future. See, the problem with many of these forms of new forms of energy is that we're relying on biological production, like plants. So what happens? Well, if you take plants and produce energy, you're just going to burn it, right? So which would you rather have? These types of energy forms, or the same for the same amount of food that could be produced on that same acre of land? I vote for food. We can get energy other ways that are cheaper, sustainable, and research in these areas is simply a way to fund a whole host of scientists that have nothing better to do with their time. So that's my soapbox. And if you disagree with me, be sure and come with evidence. End of lecture.